All right. In this section, we're going to start using the normal distribution. Prior, we discussed the empirical rule, we discussed the shape, the center, and now we're just going to actually do problems with it. And so here, we have to remember that the proportion of the population with the characteristic described is the random variable. X also can represent probability of a random selected individual. So remember that it's in terms of area where it's equal to 1 or probability, which is can be up to 100%. Either way, we're always looking for numbers between 0 and 1, right, for probability. So how do we know if something's normal? What if it doesn't tell us that it's normal? For example, what if I got all these heights in inches from random 52-year-olds, male, right? So here's 52-year-olds, boys, and their heights in inches. How would I know that's normal? I couldn't just go directly and just say, hey, it is. I'm going to do the empirical rule. So the first thing you have to do is draw the histogram. Remember, it's relative to the relative frequency of the histogram. So in part A, it says draw the histogram. So I went ahead and did that already. And we can see that if I drew a little curve here, let me get a good color. I can see that it's very nice where 36 is somehow the mean and it's a bell curve and it definitely looks normal. So what do you think? Do you think it's normally distributed? I would say yes, because the histogram takes a bell shape. All right, just commenting on the skewness. Okay, so now we would just, if it's not given to us normal, if it's raw data, we put it in our calculator or something, look at the histogram and verify it takes that bell shape. So the next thing we can do, now that I verify that it's bell-shaped, now let's talk about area. Suppose that the random variable x is normally distributed, right, with a mean mu and standard deviation sigma. The area under the normal curve represents either the proportion, right, which is area between 0 and 1, and the probability, which is also between 0 and 1. All right, well, we kind of always knew that. So, well, how does this mean for, let's just say, applications, right? This one is giraffes. The weight of giraffes are approximately normally distributed with a mean of 2,200 pounds and a standard deviation of 200 pounds. Draw a normal curve with the parameters labeled. Then shade the area under the normal curve to the left of 2,100 pounds. So the first thing we want to do is make the x-axis. Then we'll draw the normal curve as best we can. And it says I'll label the mean to be the middle, right? So 2,200. And then shade the area under the normal curve. So if they give us the standard deviation here, I'm going to go ahead and start with 2,200 and make my standard deviation marks to the left and to the right. I know I'm going to have 3 and then 3. So let me go ahead and add 2,400, 2,600, and then 2,800. And then to the left I'm subtracting, right? So that would be 2,000, 1,800, and 1,600. Just like that. So the x-axis is the parameters given, and then we would just take the standard deviation and label those three standardized values, right? 3 to the left, 3 to the right. Where would 2100 be? Well, 2200's here and 2000's here, so it would be the halfway mark right here. And then if I'm looking to the left of 2100 pounds, left is to the left, this way, and it's anything less than it, right, to the left. Okay, great. So then suppose that the area under the normal curve to the left, meaning this area here, is 0.3085. So if I took this and copied it, this left area would be 0.3085. That would be the area. So provide two interpretations of this. Okay, so the first one I would say is the proportion of giraffes that weigh less than 2,100 pounds is 0.3085. The second way is we could look at it as a probability, right? We could say there is a 30.85% chance that a randomly selected giraffe weighs less than 2,100 pounds. So you can see the difference in these two interpretations. One would say that the proportion of giraffes that weigh less than 2,100 pounds is 0.3085. But then we could say, well, if I randomly selected a giraffe, there's a 30.85% chance they'll weigh less than 2,100 pounds. We will be using both interpretations, and either interpretation is correct, but you got to make sure it's correct. You can't say proportion with chance and proportion with probability. They're very different, and the way they're interpreted is different. So as long as you can separate the two, either one is correct. Okay, but let's just say I have two samples of giraffes, and maybe one in Africa, one in San Diego, right, on the zoo. And so I have two distributions now. How can I compare? Well, we go back to standardizing the normal random variable, which is the z-score. So the z-score is again x minus the mean over the standard deviation. And we can easily standardize any by just calculating the z-scores for the x value and just having the z or the mean starting at 0. Okay, now we could find the same amount of area or proportion. This was given to us up here with the giraffes. Easily by using a table or the calculator. In this class, we're going to be using the technology, and so you would need the technology in order to do the problems in the textbook. There are examples of z-score tables that we used to use, but I just feel like we have a very powerful calculator. It's more accurate than the tables, and so I feel like we can use just the technology. Everything should just be in the calculator. And how we do that is by going to the home screen and go to second vars and distribution, and you're going to see the normal cumulative distribution function. So if you go to second vars, normal probability distribution function, and this will be a cumulative. So we'll be using the normal CDF. right? And if I wanted to do the left side of the giraffe problem, my lower will be, well, the area, remember, it tails off, it goes on forever. So we use E99 or -1, E99, just something that displays like out to negative infinity. So the smallest number that your calculator can do is -1 E99. And then we stop it right here at 2100. So let's go to the calculator. So the lower is, let me clear this out, would be, you could either do negative second E, which is this double E where the comma is. So you would do second comma 99. Or if you want to see a number, I usually put -1 second comma with the E 99. Where does it stop? Well, I wanted to know 2100 or less, right? I was told that the mean weight was 2200 and the standard deviation was 200. And you'll go ahead and paste. And notice it takes you to the home screen, hit enter, and it says 0.3085. So if I go over here to my curve, whoa! I didn't make that up. I know that's what you guys think most of the time. I made it up. I did not make it up. It is in the calculator, and this is the area underneath the curve to the left of 2100 for our curve. So the normal CDF, if you're doing area to the left, you'll have to do -1 E99. If you're doing area to the right, this is just ends up being positive. So you're just going to go move left to right. So when you enter your area, so let me go. Here. So it says when there is no lower bound, enter 1E99. There's no upper bound, use this. And then if it's in between, you would just put the values in between. And you don't have to use the z-scores. You can use the mean and standard deviation of your problem. It's up to you. It does both. So for example, if I just took IQ scores, because as we mentioned, IQ scores are popular for normal distribution. I would have a mean of 100, standard deviation of 15, and there's the distribution. And we're going to round everything to 4 decimal places. So let's go ahead and find Z when an individual IQ score is 120. So the first thing I would do is label the mean as 100. And then add and subtract 3 standard deviations from the mean. So you'll have, here's the standard deviation is 15. So this will be 115, 130, and 145. And to the left would be 85, 70, and then 55. And I just usually draw the halfway mark like that. So where is 120? 120 is about here. So if I found a z-score, the z would just be equal to x minus mu over standard deviation. So that would just be 120 minus 100 over 15. And if I put that in the calculator, I just get 1 point, I don't know, let's see. Okay, so 120 minus 100 divided by 15. 1 point, and I'll round to 4 decimal places. So 1.3333. So now let's just say I want to find the area under the standard normal curve. Ooh, standard to the left of Z. So what does standard mean? Well, that means it's standardized. So that means now the 100 now is 0. because that's the z-score. And you become -1, -2, -3, 1, 2, 3. And then I usually mark the halfway point. So let's just like align them, right? So 1 standard deviation away is 115, 2 standard deviations away is 130, and 3 is 145. So you could kind of see how they align, but one is with respect to the sample and the distribution, and this one's with respect to the standardized normal curve. And so therefore, if I wanted to find the area such that the z-score is less than 1.3333, and where is 1.33? Well, it's positive, and it's exactly where we labeled 120. And I wanted to the left of z, so the left would be here, right? All this area. So the area such that the z-score is less to 133 will be in the calculator norm CDF left bound. In this way it's no left bound, so -1E99 comma 1.3333 as the right bound. The mean, which is in this case 0, and standard deviations are counted by 1. So when you're using the standardized normal curve, this will be your mean and your standard deviation. And this will be your z-score. And mean is always 0 and always 1. That's what's nice about using the standardized, is you don't even care about what the distribution is, like over here, like with all these numbers. Mean and standard deviation is always 0, 1, 0, 1, 0, 1. It doesn't matter. Okay, so when I do that, let's go to the calculator. Let's go to second vars, normal CDF. I'm still going to the left, but now I want to do 1.3333. The mean is 0, standard deviation is 1, and we hit paste and enter. Okay, so let's just say I didn't standardize it, and you're like, it doesn't really matter, Darlene. Can you just use the mean and standard deviation they gave us? And I would say absolutely. So let's go back to vars distribution, right? Hit 2, and let's put in actually the value. Instead of the z-score, what was the value that we were observing, right? 120. So let's put in 120 for our x value instead of the z-score, and put in the actual mean of 100 and our standard deviation of 15. Do I get the same area? Does it matter? Nope. So you either use the standardized, which is the z-score 0, 1, or you can use your distribution, which is the value you're observing, the distribution's mean, and the distribution standard deviation. So these will always change, whereas with the standardized, it's always 0, 1. But you still get 0.9088. Okay, and then let me go ahead and take that picture here. I want to just make it super little. And then they're the same. Okay. And so now let's interpret this area in context of IQ scores. So if I did this, I could say that there is a 90.88% chance that a randomly selected individual has an IQ score less than 120. Okay, so that's like the probability interpretation. Or I could use proportions, right? I could say the proportion of IQ scores less than 120 is 0.9088. Either one of these is okay. Now, taking what we just have discussed, let's go ahead now and use the complement rule to find the area. So if I use this piece here as 1.33, and let me go ahead and label as I would prior. So here is 0, 1, 2, 3, negative, negative, negative. Here's the barrier. There we go. And so the complement says, well, if you found the area to the left, right, to be 0.9088, what's left over to be this area on the right? Okay, well, let's write this out. So the area of which the z-score is greater than 1.3333 is equal to 1 minus the area of the z from the z-score that's less than 1.3333. Well, that was just 1 minus 0.9088, which is equal to 0.0922. 12. Sorry. So if you ever want to find the opposite, you just subtract it from 1 because the total under the area under the curve is 1. So if it's 0.9088 here, then minus 1 will give you this little tiny tail, which is 0.0912. You don't really need a calculator for that. I mean, like normal CDF, all you need to do is subtract it from 1. So, okay, so the goal here is this example 6.7. If you want to find area to the left, you could either leave it in the distribution as normal CDF with the distribution values. If you need to standardize, you would find a z-score and then bound it by 0, 1 as the mean and standard deviation. Once you find one side of the area, one area on one side or the other from your observed value, you can just use the complement rule to subtract from 1. So you kind of can play with it. I encourage you to draw a picture. Always draw the normal curve, the mean, and then at least the value you're observing. Not maybe necessarily the 3 standard deviations, but where the mean is. Because I feel like these values here give you a better idea of where that value lies on the normal curve. But it's not required. But again, I encourage you to draw the area. It would give you much better perspective of where it's shaded and what you're looking for.